In this video, we will show a way to explain electric charge, the charge variations of elementary particles. We'll explain the fractional charges of quarks and give a model for matter and antimatter. Central to this concept is that space consists of discrete units, atoms of space. The idea, to me, originally came from Lee Smolin in his book, 3 Roads to Quantum Gravity. Elsewhere, in different papers and videos, we will show that these atoms of space are actually quanta. Now, if space exists as atoms of space, it's possible that gravity is the absorption of space by matter. So if we have a particle of matter, we would see space being absorbed into it. And space, these atoms of space, we are going to claim, for the sake of this model, actually consists of vortices that have spin. And to understand the model, we need to understand spin. We have here a representation of the Earth, and we have a North Pole and a South Pole. On the right here, we have a right hand. The fingers are curving around, showing the direction of spin, and the thumb points to the north. So let's get started. The black circle on each side represents the particle, or the point of attraction. Our spinning atom of space would be here, or here. And we have the orientation on the one on the left here, such as the north pole is faced towards the center of the particle, and the south pole is exposed. On the right, we have the opposite situation. The south pole is faced towards the center, and the north pole is exposed. We can look at our right hands, and for this particle here, the right hand has the north pole facing to the left, towards the center, and here we have the thumb facing away, the north pole is facing away. If we look at this, we see that the spin here, in each case, is complementary. They're spinning in the same direction. So we have south pole facing north pole, but the spin, because of the orientation, the nature of it, is complementary. And we're going to make the claim that the complementary spin is attraction. Let's now look at the situation where our particle, or center of point of attraction, has an atom of space connected to it. And in this case on the left, the south pole is faced towards the center, and the north pole is exposed. And on the one on the right, the south pole is faced towards the center, and the north pole is exposed. So each of these have the same orientation. The spinning atom of space relative to the center is identical, so that north faces north. And if you notice, or with our thumbs, we have our north and north. If we notice, the spin orientation, spin direction, is opposite. So we have the same sides facing each other, but the spins are opposite and opposing to each other. And we're going to define this situation where north faces north, the spins are opposing as repulsion. And now we're going to develop a notation system for our spin orientation. On the left, we're going to define the situation where the thumb faces towards the center of attraction, the north faces the point of attraction, and the south is pointed away. We're going to define that as a negative orientation. And we're going to, instead of drawing a little picture, we're going to use a U. And the idea of the U, say versus the end, which we'll look at here, the U doesn't have anything on the top, so that makes a kind of a convenient way to define a negative orientation. On the right, we have the north pole facing away from the center or point of attraction, and the south pole faces towards it. So if the north pole faces away, we're going to use an N. And of course, just the opposite of that, we have a positive situation here. So a U indicates a negative orientation towards the center, and an N indicates a positive orientation. Now we have a critical assumption to make here that works really well. From our point of attraction, the center of the particle, we're going to make the claim in this model that there are 6 sides, sort of like a cube. If you think of a cube, there are 6 sides to a cube. And so we can go up, back, left and right, and up and down, and outwards and into the screen. And here on the right, we have our point of attraction. And we can have, in this particular case, all the orientations are the same. We have our U's, because the south poles face towards it. And rather difficult to draw. Coming off the screen, we'd have a U, and going into the screen, we'd have a U. But doing this in 3 dimensions is tough to draw. So we're going to make it easy and do it in 2 dimensions. So this is a 2-dimensional representation of our 3-dimension realistic model. We're going to put them all on a plane. And instead of coming in and out of the screen, we're just going to fit 6 around the sides. And here we have our point of attraction in the center, and we have 6 U's going around it. And since this has 6 U's, we could call this a 6U. We can also change the orientation of one of them so that we have 5 U's and 1 N. So we'd call that a 5U and 1 N. And I'm not going to draw all the pictures, but we just drop this down to a 4U and a 2N. Of course, you could have a 3U and a 3N. And you could have a 2U and a 4N and a 1U and a 5N. And finally, you could even have a 6N, where the orientations are all N's going around it. Okay, if we take our 6U orientation, and the U, remember, is a south pole facing out, and we've defined that as negative, we can write it just like we would type it. Just that's kind of the nice things about using the U and N notation. We'd have 6 U's, we could just write them out. And we're going to define this as a -1 charge. Now in the case where we have 5U and 1 N, we've taken one of the U's and swapped it so that it's positive orientation here. We could write 5 U's and 1 N. Now notice that the 1 N and 1 U can cancel out, so that we have a total of 4 out of 6 are negative. And we're going to define this as a -2/3 charge. Next, we could look at our 4U, 2N orientation. So you have 4 U's and 2 N. The 2 U's and 2 N can be said to cancel out, so that we have 2 out of the 6 atom space orientations as being negative, because that's the negative end. So we would define this as a -1/3 charge. Here on the bottom, we have 3U, 3N. They all cancel out, so the net charge here would be 0. Okay, in this table, we're going to start at the top row. We have a 6U orientation. The negatives all face outwards. We would write it as 6 U's. We've defined that to be a -1 charge, and that matches the charge of the electron. If we take a 5U 1N configuration, we get a net charge of -2/3, which matches the anti-up quarks charge. A 4U 2N configuration, we have canceling out. The underline here means these have canceled out, giving us a net of 2/6, or -1/3, and that matches the charge of the down quark. With 3U, 3N, they all cancel out, and we get a 0 net charge, and that matches the neutrino. A 2U, 4N configuration gives us a net of 2/6 positive, or +1/3, which matches the anti-down quarks charge. A 1U, 5N, cancel out, leaves us a positive charge of +2/3, matches the up quark. And finally, our last orientation, all 6 are N, gives us a +1 charge, and that matches the positron. So looking at this table, in the big picture, our numbers of orientations give us net charges that match that seen within existing elementary particles. It's an amazingly simple system to produce the electrical charges seen, the fractional charges and the antimatter charges. Now if we take our 6U orientation, which we define as the electron, and put it up next to a 6N orientation, or positron, we'd find that all 6 points of attachment on each particle are complementary. So the spin orientations would match, and there would be nothing to stop the particles from being pulled together. And we could define this as the basis of antiparticle annihilation. Now we've just looked at what happens when you match the electron against the positron. You can connect all 6 on the electron to all 6 on the positron in such a way that there would be complementary spin and therefore annihilation. We can do the same thing with a 5U and 1N of the anti-up quark and the 1U 5N of the up quark, and we're able to match all 6 on each particle, so they would also draw together through complementary spin. The same thing goes for the down quark and the anti-down quark and the neutrino and the anti-neutrino. So with our model of matter, where an atom of space is a spinning atom of space and it's being drawn in towards the elementary particle, it's very easy to explain matter and antimatter. And it's all based on which way the atom of space is oriented towards the particle center. And we can explain fractional charges just as easily. If we look at our 4U 2N arrangement, we can write it out as such, and we see that the 2U and 2N over here cancel out, giving us a net charge of -1/3, matching the down quark. So fractional charges are also very easy to explain with this simple model. Using these charge arrangements, we can construct the neutron. The neutron consists of a down quark, and one up quark. Now, we've made a little triangle here. This is like the center. So we have 1, 2, 3, 4U and 2N. And over here, the same thing. 4U's and 2N. And down here is our up quark. We have 1, 2, 3, 4, 5 positive orientations and 1 negative on that elementary particle. And we find we can connect spin orientations, complementary spin orientations between all 3, such that the negative charge and the positive charge will cancel out, leaving us a net 0 charge. And you notice too that no one particle can be drawn towards another fully without running into opposite spin arrangement. And we can also construct the proton using our model. We have 2 up quarks and a down quark, and we can tie complementary spin orientation on all these lines such that there's a net of 6 positive orientations left within the 3 quarks. And from our 3 quarks combining to form a proton, we have 6 unmatched positive charges, and they're available to binding to the 6 negative charges of an electron. Looking again at our model of the proton, we have our 5N 1U and 5N 1U and 2N 4U, giving us a total of 12N and 6U. The net would be 6N. But notice too that within the proton in this model we have 6U, 6 negative orientations. This is identical to the charge of the electron. And this leads to the thought that the reason the electron cannot fall into the proton is because of the existence of negative charge within the proton. It's hidden in there. So this simple model gives us a basis for electrical charge. It gives us all the charge variations seen in particles. It gives us fractional charges, explains antimatter, and tells us why the electron is not pulled into the proton despite the full positive charge. For more information on this and many other topics, please go to jimtasano.com.